Good evening, everyone. Welcome to NPTEL tutorial session for the course Essentials of Oxidation Reduction and Carbon-Carbon Bond Formation Application in Organic Synthesis, taken by Professor Yashwant D. Vankar, retired from Chemistry Department, IIT Kanpur. So, this is our fifth tutorial session. So far we have been discussing up to week 4 lecture contents, related topics, and the mechanisms of the reactions, as well as we have solved several problems, including the assignment problems until week 4. So today in this session, we will be firstly discussing the week 5 lectures. We will have a discussion on the topics discussed in week 5 lecture, and then we will move ahead to solve week 5 assignment questions. So, in the last lecture, the final topic which we discussed was about Barton reaction. So, we will first have a recap on the last lecture. So, in Barton reactions, we saw that the abstraction of this delta proton happens for this type of compounds, and it will. So, firstly, this alcohol will react with this NOCH to form this kind of intermediate, and then under photochemical reaction, this cleavage of this NO radical will happen, and that NO radical will leave, and this alkoxy radical will be forming. Then after that, this delta hydrogen abstraction will take place to form a six-membered cyclic transition state. So once this six-membered cyclic transition state is formed, after that what happens? This proton will come over this oxygen and it will result in this radical. Then this alkyl radical will then combine with this NO radical to form this compound. So this is the final product which we will get in Barton reaction. Then we have also seen several reactions associated with this Barton reaction as well. Then another example here is this hypoiodides can be readily generated from the alcohols upon reaction with iodine in presence of lead tetracetate, mercuric oxide or phenyl iododiacetate. So what has happened? This type of compound upon treatment with this iodine and phenyl iododiacetate, what is happening? Firstly, this bond will cleave and this O radical will form here. Then that will abstract proton from this delta position, that is from this methyl radical, and that two radicals will combine to form this kind of intermediate. Then another similar reaction is happening between this one and this one, that is through that six membered cyclic transition state we will get this type of intermediate. So here the reaction is happening through this kind of intermediate. So firstly, when this delta hydrogen is abstracted by this oxygen radical, that iodine radical will combine with the CH2 radical and form this kind of intermediate. Then this will form a cyclic transition state and Hi will leave, and this will form this bond between CH2 and oxygen will be formed. So this is a modification of Barton reaction. Then another example is the specific deprotection of benzyl ether, which is done like this. So this one, when upon photochemical condition, firstly it will form this radical. that will abstract this hydrogen radical from this benzyl group, and it will form this radical over here. Then what will happen, this bond will cleave again, and this oxygen radical will combine with this oxygen radical, and that will give this compound. So when we deprotect this, we can selectively deprotect this benzyl group only without affecting any of the other benzyl group. Even the primary will be remaining intact. So this is another example or another application of Barton reaction. Then some modifications of Barton reaction involve this beta cleavage instead of this proton cleavage or alpha cleavage. So in that case, what is happening? Firstly, this oxygen radical will form where this proton is getting cleaved, and then what will happen? This bond is breaking, so radical will form here and over this center. So this two radical will combine to form this ketone, and then this bond is breaking. So here it will be double bond, and then this bu3sn radical will eliminate, so we will be getting this product. So this is also another modification of Barton reaction where we are getting beta cleavage instead of delta hydrogen abstraction. So, if the beta cleavage leads to carbon radical situated alpha to an oxygen or a nitrogen atom, then an oxonium or iminium ion can form, which gets trapped by nucleophile as exemplified. So, as we can see here, this oxygen radical is firstly formed, giving rise to this compound. Then, what is happening? Then what is happening? So then this beta cleavage is happening. So here radical is forming, here radical is forming. These two radicals will combine, and here double bond O will form, and here it will be this radical. Then once this is formed, when this is oxidized, this will be becoming this particular oxonium ion, and then what will happen? This nitrogen lone pair will attack over this oxonium ion, and this positive charge will get quenched and give rise to this compound. Then which upon deprotection of or removal of this ester group as well as this hydrolysis will give this particular derivative. So this is another example for beta cleavage. Now another example here, it is given specific conversion of alcohol to aldehyde without over oxidation to acid. So one of the drawback of the oxidation reactions are that is that so we cannot control the oxidation reaction. Mostly this alcohol will be getting oxidized to acid, passing through aldehyde of course, but we cannot control that at this um, aldehyde stage. So that is one drawback of many of the oxidation. So one of this oxidation which can control the oxidation up to this aldehydic stage is TPAP oxidation, which we already saw, tetraisopropyl aluminium ammonium ruthenate. So in that case we can see this primary alcohol is getting converted into aldehyde, and here also using IBX DMSO condition, this primary alcohol is getting converted into the corresponding aldehyde. And here what is happening under this condition? So at first this tosyl tosic acid, that is paratoluene sulfonic acid is deprotecting this O-trityl group, so it will be OH, that is a primary alcohol will be there. Then DMP is oxidizing this primary alcohol into the corresponding aldehyde. So this compound is extremely sensitive to acid, so DMP is a very mild reagent which we can use at this situation. And in all these cases, as we can see, the reaction is stopping at the aldehydic stage and it is not going into carboxylic acid. Okay, so another alternative reaction for this conversion of alcohol to aldehyde is tempo oxidation. So tempo is tetramethyl piperidine nitroxy, this radical compound, that is tempo. So tempo upon treatment with this alcohol in presence of this NaOCl and KBr will give this particular aldehyde and it is not getting oxidized into the ketone. So here NaOCl and tempo are real oxidants and KBr is used because in the intermediate we can see a chloride salt is forming. So because of the low solubility of the chloride salt we are using KBr so that the corresponding chloride will be converted into bromide. Bromides are mostly more soluble in organic medium, so chloride salt is less soluble, so that's why we are using KBr. So here what is happening, firstly oxidation of this tempo by using NaOCl will give this particular intermediate. Then in the presence of alcohol, this oxygen lone pair will attack over this nitrogen, this bond will shift over here, which will give this intermediate. Then what will happen, this O minus will take up this proton, this bond will shift over here and this will go to here forming this compound and this our product aldehyde. Then this can again be reoxidized by this NaOCl to get this intermediate and this reaction carry forward. So tempo is needed in catalytic only 1 mole percentage. NaOCl is needed in stoichiometric amount. Now, the another oxidation for the conversion of aldehyde into carboxylic acid is pinic oxidation. So, pinic oxidation, what is happening? We are using this NaClO2, tertiary butanol, and NH2PO4, and this one alkene. So, here what is happening? Firstly, this NaClO2, that is Cl2 minus, and this hypophosphate H2PO4 minus will form HClO2 and HPO4 2 minus. So, this is the active species in the pinic oxidation. So, what will happen? This aldehyde will get first protonated by this HClO2, so it will form this compound. Then this O minus is attacking over this carbonyl carbon center, and this positive charge will be neutralized, and we will get this intermediate. Then, of course, what is happening? This oxygen lone pairs will take this proton, it will come over here, and this will eliminate to form this HOCl and this acetic acid. So, acetic acid or whatever acid. So, as we can see, here NaClO2 is used, H2PO4 is used, tertiary butanol is the solvent. Then what is the role of this particular alkene over this reaction? So that is used for quenching this HOCl. So this HOCl, if present in the reaction medium, can lead to some side reaction. So for quenching that, this 2-methyl to butene is used. So that will undergo addition over this alkene, and it will form this compound. So this will be another byproduct in the reaction. Instead of HOCl, we will be getting this particular byproduct. So, pinic oxidation has proven to be both tolerant of sensitive functionalities and capable of reacting with sterically hindered groups. So, that is one advantage of pinic oxidation. It can tolerate various sensitive functional groups, and it is capable of reacting with sterically hindered groups. So now we can see some examples for this pinic oxidation where this aldehyde is converted into corresponding acid, and here instead of this 2-methyl to butene, H2O2 is acting as the acid scavenger. So H2O2, what it will do? It will convert HOCl into HCl, H2O, and oxygen, so that the side reactions will not take place. And here, as we can see, these benzyl groups are intact, ester is intact, epoxide is intact. Only the acid aldehyde is getting converted into corresponding carboxylic acid. Now, another oxidizing agent or organic oxid or bio mediated or oxidation reaction is carried out using the Pseudomonas putida, which is a gram-negative rod-shaped saprotrophic soil bacterium. So it is found in mostly soil and water habitats where there is oxygen, and its optimal growing temperature is 25 to 30 degrees Celsius, and it can be easily isolated. Then it is having several strains, including this KT2440 strain, which is having a mutual relationship between this plant and bacteria. So a symbiotic relationship it is carrying out. And this mutant 39 bar D leads to the dihydroxylation reaction. So what is happening with this type of aromatic compounds can be converted into this type of cis diols by using this particular bacteria. So then this cis diols can be utilized to synthesize various natural products and biologically important molecules. So here also we can see this can be converted into this cis diol, which can be used for the conversion into this particular compound. Here also this can be used for the conversion into this particular compound. So these are its applications. So this is the main reaction which is carried out by this bacteria. So one synthetic application of this type of oxidation we can see. So if we have this compound, this can be converted into this two natural product plus conturitol F and minus conturitol F. So that is this plus conturitol F is a potent glycosidase inhibitor. So how this reaction is happening? So once we get this diol, this both the hydroxyl groups are protected into using this carbonate to get this compound. Then MCPB oxidation, if it is going over here, since this is beta, this epoxide will be coming over alpha, so we will be getting this compound. If it's going over here, we will be getting this particular compound. Then what is happening? So this can be written in this form also. So either this will form or this will form. Then what is happening? This protection of this or this hydroxyl oxygen lone pair will attack over this center because of this double bond also, and epoxide will be opening and it will give this product. Similarly, from this we will be getting this one. Then the removal of this particular protecting group and this carbonate will give plus conduritol F, and from this we will get minus conduritol F under this Birch reduction condition. So this is one synthetic application of the oxidation carried out using this Pseudomonas putida. Then here another example is this diol. Once we get from this chlorobenzene, it is protected using this dimethoxy compound to get this derivative. Then ozonolysis of this one will give. So this both the double bonds will be cleaved. So what we will be getting is this Cl, here C double bond O, and here also C double bond O will form. Then this protection, then it can cyclize to form, it can cyclize to form this compound. Then so this is basically acid over here and aldehyde over here. So this is again oxidizing into the corresponding acid, so we'll be getting this one. So this acid is getting esterified using this diazomethane to get this compound. Then upon this Grignard addition, this 1 2 addition, what is happening, this it's adding over the aldehyde. So it will add over this aldehyde, alcohol will form, that oxygen lone pair will again attack over this, OMe will leave, and we will get this compound. Then again osmium tetroxide NMO will give this diol over here, and NaBH4 will reduce that to give this corresponding alcohol here. So that is another synthetic application. So here we are seeing one particular reagent and its mechanism of action, how it is working, and then its synthetic applications, how it is being exploited or used in the organic synthesis of various natural products or biologically important molecules. Now, this is another example, that is, this particular diol is protected as this one. Then, what is happening upon treatment with this complex? Directly, this one of this double bond is getting converted into the corresponding acidity derivative. Then, using this tributyl tinhydride and AIBN for the removal of this bromide is giving this compound. So, this is an advanced application or an advanced reaction. So, how this is traditionally carried out? Firstly, this NBS mediated bromination will happen over this double bond. Then water will open that bromonium ion to form this compound. Then conversion of this NaN3 will be attacking over, like substitution will happen through this epoxide formation. So then NaN3 will attack over this. So this is beta, so NaN3 will attack over the alpha phase to form this compound. Then methylation of this group will give this O methylate, and then LH reduction will reduce this into NH2, and that will attack over the center. OMS will leave to form this acididine. Then tosyl chloride for this protection of this NH, and tributyl tinhydride AIBN for this bromide. So this 1, 2, 3, 4, 5 steps are carried out just by using two steps. That is an advanced application. Both are starting from the same aromatic derived cis diol. Now we will move on to reductions in organic chemistry. So that was about the oxidation reactions. We have seen many oxidizing reagent. So now commonly employed reagents for carrying out reduction is NaBH for sodium borohydride, and LAH, that is lithium aluminum hydride. So this type of ketone can be converted into this corresponding alcohol by either using NaBH for reduction or LAH reduction. Now, if we are doing this LH reduction on alpha beta unsaturated ketone, we can get this allylic alcohol or completely reduced product or only the double bond reduced product. So NaBH4 is mostly used at low temperature, and for NaBH4 reduction, ethanol and methanol are normally used, but for LH reduction dry THF diethyl ether 1 2 dimethoxyethane are commonly used. So this NaBH4 is comparatively mild. So although this alcoholic solvents like with methanol and ethanol, this LAH also reacts, but NaBH4 also react, but NaBH4 reacts more slowly, and hence it can be used as a reagent in methanol or ethanol. And LH is very sensitive reagent. It reacts violently with H2O, causing fire. So hence dry moisture free solvents are always preferred with LH. Now, LH can react with this ketones to give this alcohol. It can react with acids or esters to give the alcohol. Then it can give it nitrile to give corresponding amine, nitro to give amine, acid to give amine, alkynes to give this transalkene. And even with lactones, it will give this completely reduced product that through the lactol intermediate, again lactol will undergo reduction to give this diol compound. So with epoxides, what is happening? It is giving this type of alcohol. So it is working in an SN2 fashion. That is, it is attacking over here. That hydride will attack over here, this center, and this will open to form this kind of compound. Then if this we are using, it will attack over this center and it will give this type of alcohols. So here also same thing, it will attack over the SN2 fashion, means it will attack over the less hindered position. It will attack over the less hindered position and give this alcohol. Now, steric factors can be increased by putting OR groups both on NaBH4 and LiAlH4, like NaOR thrice BH, or lithium aluminum hydride derivatives like lithium alkoxy aluminum hydride can be prepared and used effectively. So rate of the reduction keeps decreasing as the number of OR groups increases. So we can control the reaction and the reactivity of the reducing reagent if we increase the OR groups on either NaBH4 or LAH. Further, better stereoselectivity can be also obtained with sterically bulky reagents. So here as we can see, this ester is getting converted into alcohol, which is happening through this aldehyde. So first what will happen, firstly this uh, with this ester O minus, this lithium plus will coordinate and this ionic intermediate will form. Then this aluminum hydride will attack over this and it will form this kind of intermediate. Then what will happen, this AlH3 will take this proton and this bond will shift over here and this will leave, so giving this aldehyde. Then same thing will happen and reduction again to give this alcohol. So aldehyde is more reactive than ester, that's why aldehyde is again getting converted back into alcohol. So this is the mechanism of LH reduction of nitriles that I am not going into the detail, and these are some example. Then we have seen another reagent, that is dibalH, which is a trivalent aluminium and thus Lewis acidic as opposed to LH, which is tetravalent and thus nucleophilic. So here we can control the reaction by using DCM or THF where DCM or toluene will be acting as non-participating solvent, but THF will be like a participating solvent, and it will help in stopping the reaction at aldehydic stage. Not aldehydic stage, it will stop the reaction at the alcoholic stage. If we are using DCM or this toluene, we can stop the reaction at the aldehydic stage. So then ester can be reduced, ester and lactone can be reduced. Even we can stop the reaction at the aldehydic stage as well, or lactol stage as well, and the alcohol stage as well. Then nitrile and alkyne reduction. So as we said, this LH will be giving trans alkene, dibal H will be giving cis alkene. It is due to the difference in the intermediate, where LH will be going through this ionic intermediate. Firstly, lithium will coordinate with this alkene, then hydride will be attacking over the opposite side. But in the case of diballage, this aluminium and this hydrogen will be attacking from the coordinating from the same side, so that will give cis alkenes. Then we have seen some more examples of this dibyl reduction and how it is used for the conversion of vainrabamide into the corresponding uh, aldehydes. Then we have seen some more examples for that. So then if we are using LAH in combination with this AlCl3, we can control the reactivity, so that will form this mixed chloride hydride type of reaction. So that can be used to convert this. If we are treating this particular compound with LAH, it will remove this bromide as well as reduce this ester to give this alcohol. Then if we are using LAH and AlCl3, it will only reduce this ester and without affecting this bromide. Then another reducing reagent is red aluminium, that is reducing aluminium, which is basically sodium bis 2 methoxy ethoxy aluminium hydride, which is also known as Witride because it was first prepared by Wit. And it is stable in air and reductions are comparable with LAH. It is soluble in aromatic and aliphatic hydrocarbons and in ether due to increased hydrophobicity. So this red aluminium can reduce this only this double bond in the presence of this copper bromide. So this here the expected mechanism is this copper hydride species can form. So copper hydride, as we know, it can act as a soft center and it will undergo this 1,4 addition rather than the 1,2 addition. Same thing is happening with here also. Only the double bond is getting reduced. Alpha beta unsaturated ketone is converted into the corresponding ketone. Then these are some examples of dibalh. Then if in the case of this epoxide opening, we saw that LH, in the case of LH, it is SN2 addition. So from the less hindered position, it will be attacking. So like this, intermediate is forming first, then hydride will attack like this, it will open here. But in the case of dibalh, it is intermolecular reduction. So H is attacking over here, and this is coordinating with this aluminum, and epoxide is opening. So in the case of LAH or red dal, this 1,3 diol will be major. In the case of dibalish, this 1,2 diol will be the major product. Then this Lucci reduction, that is basically 1,2 reduction of this alpha beta unsaturated ketone. So without affecting the double bond, only the ketone is getting reduced. So specifically, it is being carried out by using NaBH4 and the cerium chloride uh, complex. So lithium plus and copper plus will be giving this completely reduced product. Cobalt 2 plus and Na2 plus will be giving this one along with this starting material and this completely reduced product. So what NaBH4 will do is only ketone is getting reduced. So that is happening through this intermediate. And this, I think, mostly about this, it is discussed in the week 6 lecture content. So that we will see in the next session. And so before winding up, we will have a discussion on the week 5 assignment question. So the first question was major product that will form in the following reaction. So this particular compound upon treatment with MCPBA and then this alcohol and HBF4, which will be the major product here out of the four options given. So here what is happening, firstly this MCPBA will carry out epoxidation. So since this whole group is above, epoxidation will undergo through the alpha phase and give this epoxide. Then nextly this alcohol will attack, this oxygen lone pair will attack over this alcohol at this position, and this will open up and give this particular compound. So this HBF4 is helping in this reaction by coordinating with this epoxide, or by protonating this epoxide. Now, the next question, the major product that forms in the following reaction. So, this particular epoxide upon treatment with this LiAlD4, that is this tetradeuterium derivative of the lithium aluminum hydride, which will be the major product here. So here the correct answer is option 1. So as I said earlier, this opening of epoxide will be an SN2 reaction. So it will happen from the less hindered side. So the hydride or the deuterium corresponding will be attacking over this less hindered position, and epoxide will open from this side and it will give this product. So reduction with LiAlDF4 will occur from the beta side at the carbon, which has a methyl substituent. Now moving on to the next question, that is in the reduction of ester with LH, the tetrahedral intermediate that will not form among the following is, so here are three options. So out of these three options, which compound will not be, or which intermediate will not form by the reduction while reducing this this phenyl ester with LH. So here the correct intermediate is 1, 2, and 3. So this is not an intermediate which will form. So this is the first intermediate that will be forming. Then that will convert into this one. This aluminum hydride will attack over this oxygen and it will form this intermediate. And then what is happening? This hydride again will attack and OET will leave to form this intermediate. So structure of the intermediate in option 4 will not form during the reaction, as the negative charge will not be forming at the carbon atom. So lithium cannot be coordinated with the carbon. So hence option 4 is the correct answer. Now, moving to the next question. In the following sequence of reaction, the major product that will form is, so this alkyne is first treated with dibyl H, then methyl lithium, then carbon dioxide, then hydrolysis, and then diazomethane. So, which will be the major product out of the four options given here? So here, what is happening? Firstly, this dibyl H will reduce the alkyne into corresponding cis alkene. Then methyl lithium will make a trivalent aluminium into tetravalent 8 complex, which will react with carbon dioxide. So we saw this example that will be converted into the corresponding cis acid will form. Then upon treatment, so that will happen until this condition. So the dibalage will reduce alkyne in cis fashion, then trivalent aluminum will form. Methyl lithium will make the trivalent aluminum to tetravalent 8 complex, which will react with the carbon dioxide to form the corresponding cis acid. Then that carboxylic acid will react with diazomethane to form the ester. So this will be the cis ester derivative will be the product. Option 4 will be the answer. Moving on to the next question, the major product in the following reaction. So this particular compound upon treatment with this dibalH and in the next step with this NaClO2, tertiary butanol and this NaH2PO4 and 2-methyl 2-butene. Then in the second step with lithium aluminum hydride, which will be the major product here. So here what is happening, this is a Weinreb-amide. So firstly dibar H will convert this Weinreb-amide into corresponding aldehyde. Then pinic oxidation will convert that aldehyde into the corresponding um, carboxylic acid. Then LAH will reduce it into the corresponding alcohol. So the correct answer would be option 2. Starting compound is a Weinreb-amide. Dibar H will reduce it. Corresponding aldehyde will form. Pinic oxidation will make into acid, and LAH reduction will give the alcohol. Now, the next question, in the following sequence of reaction, one of the key intermediates is, so this acid chloride upon treatment with this methyl methoxyamine K2CO3, then this alkyl lithium, and then hydrolysis will give this ketone. So, which is the reagent intermediate for this reaction? One of the key intermediate for the reaction. So here what is happening? Firstly, the preparation of Weinreb-amide is happening. Acid chloride with this compound will form the corresponding Weinreb-amide. Then presence of NH in the reaction of NH in presence of K2CO3 would allow nucleophilic reaction to occur onto acid chloride. Then Li plus from R1 Li will first coordinate with the two oxygen followed by nucleophilic addition. So this R1 Li will that attack over that Weinreb-amide, and it will give this particular intermediate after the hydrolysis. So upon acid hydrolysis, it will break and release the ketone as the final product. So the correct answer would be option 4, which is formed by the option 4 is formed by the after forming this Weinreb-amide, this alkyl lithium will attack over that. This alkyl group will attack over the Weinreb-amide, and oxygen will coordinate with lithium to form this particular intermediate. So option 4 will be the correct answer. Sorry for that, I lost my network connection. So this would be the correct answer would be option 4 for this question. Now the next question, in the following reaction the reagents A and B are respectively, so this Weinreb is converted into this compound, so which will be the corresponding reagents required for this transition. So here, as shown here, firstly, what is happening? The deprotonation of this particular compound. Answer is this compound 4. Deprotonation of this particular CH2 will happen, and then by the butyl lithium, it will attack over this Weinreb and this group will be eliminating to form this compound. So the correct choice of the reagent is option 4. Deprotonation with butyl lithium will lead to the corresponding anion, which will react with the Weinreb via an enolate to form a carbon-carbon bond as a chelate compound, which upon hydrolysis will form the beta keto ester. Now the last question, the major product that will form in the following sequence of reaction. So this particular compound upon treatment with LAH-AlCl3 in the first step, then with PCC, then with this PPH3, then NaH and then warming, which will be the major product. So here what is happening, first the selective reduction of ester is happening in the presence of this bromide because we are using a combination of LH and AlCl3. So this will give the corresponding alcohol over here. Then PPH3, no, PCC will oxidize it into the corresponding aldehyde. Then PPH3 will react and form this phosphonium salt, which upon treatment with NaH will give the ylide, which can undergo intramolecular Wittig reaction with this aldehyde to form this compound. So the correct answer would be option 1. So that's about the week 5 assignment question. So with this we will conclude today's session. So today so far we have discussed the week 5 lecture contents and week 5 assignment question. If you have any doubts or any clarification you need regarding any topics or any content or any question discussed today, please feel free to ask. So we will see you in the next session, which will be on the next Saturday at 5 o'clock. Thank you for joining and thank you for listening. Thank you.